Bioradar. What is our future with Bioradar? That is basically what I want to highlight on. And obviously, I'm also going to demonstrate to you what is a bioradar, why do we at all should be concerned about it. So let's see. First of all, the future that we are talking about, we want our future to be compact, connected, and coordinated. These are three terms that come up many times when we look at the future, when people describe what we really want for our future. We want the devices to be compact. We want them to be connected. We want our lives to be connected through particular devices, and then coordination. Coordination is very important in a lifestyle which is fastly progressing. We are progressing, we are moving ahead in a very fast manner. So coordination becomes very important. So with this type of a future in our view, the first thing that comes up is there are three words which start with C, and first thing that comes to your mind is communication. So what type of communication? You are all very much familiar with this wireless communication term, and this webinar, this course, in fact, I believe is on wireless communication. So wireless communication. Now, when we talk about wireless communication, where does radar fit in? That is the question. In all the topics that you are looking today through this entire week, there is a lot of communication, but how is radar related to this particular area? So let's look at that and let's see how radar will benefit us in this. But the problem is, whenever you hear radar, the first pictures that come to your mind are pictures that I'm showing here. The first picture is that of a military radar. And it's a huge structure. So you obviously will say, well, this is no way compact. Yes, true. This is not compact. And this is obviously benefiting our society as a whole, but not in the personal communication range. So how do we at all progress forward to look at radar as a bioradar? That's one question. The second picture on this slide actually shows a weather radar. The weather radar here, so this weather radar here that we are seeing is also very, very huge structure. It's larger, in fact, and what it does is, we are all aware of that. We every day or every week we will at least open the weather app once to check what is coming, what is the next week's happenings in terms of the climate, in terms of the weather. So this is something that helps us. Definitely it helps us in a lot of ways, but not in the way that we are thinking of staying connected and coordinated. So how do we at all modify this type of radar and move forward to talk about it as a bioradar? So that's the first thing that we need to understand. For understanding that, another terminology that I will talk about briefly is something that you oftentimes abbreviate as SDR. So SDR stands in general for software defined radio. And it is a common term. Software defined radio has been in use for the last few decades at least. And most of you must be knowing the benefits of such an SDR. Now, derived from the same principles, we currently are using what we call as software defined radar. So software-defined radar will benefit us in translating the large structures that we use for the military or for the weather or for some other satellite purposes, interspace purposes, to what we need for our personal use. That is the particular topic here, the bioradar. So what is that? In a software-defined radar, basically we change the hardware components. Here in a traditional radar, we have hardware components. What are the hardware components that are required? The same as you would use in any communication system, such as the mixers, the filters, modulators, demodulators, detectors, etc. These are very standard components in a communication system. So when we say it is software defined, what we basically do is we exchange all these hardware components, we throw them out of our board and we implement them on a software. And this software is placed either in a computer or it can be placed in a standalone programmable device like an FPGA. And once that is done, we will call that a software-defined radar. And what is the benefit of that? Obvious benefit is that it can be controlled adaptively. And once we can control this particular device adaptively, we can use it for many, many purposes at a time. So it is no more a single-use device. We can modify it for our benefit. We can modify it for our application of the day. Let's say today you want to detect heartbeat. That can be done for today. Tomorrow you are no more interested in a heartbeat. You want to detect your motion, your fall. So we can adaptively change the radar and make it suitable for multiple purposes at a time. So when that is possible, then comes this concept of the bioradar. So bioradar is basically a technology which combines the radar with biosensors. So we have radar on one side, we have biosensors on the other side. A radar which deals with sensing on the biological sense is a bioradar. And biosensing doesn't necessarily mean it's related to your health. It can be related to your security. It can be related to your convenience. It can be related to multiple spectrum at a time. So let's see some examples of this bioradar first before I go into more details. Here is actually a laboratory setup which we sometimes use for detecting the particulars of a person, a subject. And the radar, why I put this picture up, if you notice, the radar is a very, very tiny device which can be mounted on any kind of a tripod. It could be mounted on a wall. It could be mounted anywhere you would like to. This is the larger view of this radar. And here we have antennas, we have all our components that are required, and obviously we have an FPGA which is programmed. It is programmed to detect certain aspects of this subject. So this is a setup that could be used for the research in bioradars. On the field scenario, these are already used in certain applications, or they are getting more and more applicable, let's say. Here is a scenario wherein you see this is a testing going on. This is the radar. It's the dimension of this has been enlarged for view. It is placed somewhere in front of a wall, and a person is standing behind that. And the purpose is to be able to detect the persons behind the wall. So this is also a type of bioradar. Some of you may already be aware of the term true wall radar. So that falls under this category of bioradars. So this is an application. We'll discuss a bit more into this. Then here you see another application of this technique. And this is basically showing the it's an NICU. So here the incubator you can see, and on top of that there is a radar fitted. This small device here, the white color device at the top where I'm pointing, is actually the radar. And the purpose of this is to be able to track the patient's vital information, because when we have this NICU where the newborns are kept, we can't really hook them up onto a multitude of sensors. So nowadays there is a large push forward for implementing this bioradar in this NICUs and both ICUs also. That will basically be much, much less unpleasant for the patient. And also it has shown a very good accuracy in terms of vital signs detection. Then on the other spectrum, if you focus on this picture at the bottom, there is this connected car information that you may be hearing. We are talking all the time of automated driving cars. And these automated driving cars are obviously focused on multitude of sensors, including radars. But in terms of bioradar, there is also the particular help by which we can detect the driver's health. So sometimes the driver falls asleep. How does the car actually be aware of that when we are talking about automated driving? It is very natural for the driver to fall asleep, and you may have heard that there have been a few accidents on that line already. So there is this particular system that has been proposed, and the picture of that, this is actually a small version which I have shown. It's a FMCW radar for it's a MM wave radar. Means this is operated in the range of 77 to 80 gigahertz. So this particular radar will be able to detect obviously the surrounding outside the car, also what is happening inside, whether there is the driver who is having a particular health issue, maybe an emergency maybe there. It can also detect whether there are persons sitting inside the car or not. So there is a particular use which we are already seeing inside these cars. Even if the car is not on automated driving mode, these have shown a lot of usage, a lot of applicability. So bioradars are also useful in the automobile industry. So these are some of the applications. I'm going to go forward and give you in a more systematic manner the applications that we can think of. So first of all, why radar? Why at all radar is used? You know these things for I think already. So let's refresh. Why do we at all use a radar? Because it has got a all-weather operation. This is a very, very important part. It is an all-weather operation. We can't use a camera because it doesn't have an all-weather operation. Night vision cameras are there, but they also have their own limitations. These radars are also useful when the weather is inclement, means it's raining, it's foggy, so we can detect through that. Then radars are particularly known for their long range, and this is one of the primary uses of radar. However, for bioradar applications, we are not much concerned about the range because it is in general a short range application. Then radars have a wide area search capability, which is very, very important. Let's say I want to use this bioradar in my house and I want to detect the heartbeat of a person inside the house. It's called health monitoring. So when we want to do that, obviously we need to have this radar to be able to search over the entire room and be able to find the subject. So wide area search capability is there. Then it detects and tracks moving objects. Doppler radar, if that is a term that sounds familiar to you. Doppler radars are used for tracking vehicles, for tracking aircrafts, and they also are used nowadays for tracking human beings. So this is the detect and track moving objects. And finally, it is possible to get very high resolution images based on this radar technology. So this is where the radar fits in, where we do some kind of MRI, let's say some kind of health checkup we came to do. That can be replaced by the radar, although that is still a research in progress, but there is a very good possibility that someday we will be able to replace that, the X-rays and the MRIs, with the help of a more compact version of the radar. So these are some of the reasons why radars are popular. And this is a particular scenario in which you may be identifying a radar in aircraft moves in, the radar sends its signal, and on the other hand, the aircraft sends back a signal which is detected by another antenna or another radar unit, or it can be detected by the same unit depending on the mode of operation. Now for the bioradar, we have a human, so there is the antenna which will send the signal to the human being, and this human being, whatever the reflection he or she will generate, it will be received by the corresponding receiver. So this is the simplest way of looking at a bioradar. Now we said that the future is supposed to be compact, connected and coordinated. So let's see if radar is able to do that. So we can be able to achieve continuous sensing with this radar, this bioradar. So what is continuous sensing? It is real-time and continuous monitoring of the vital health parameters of the persons at risk. So it's called continuous sensing of the health parameters. Then there comes connected sensing. Connected sensing basically refers to the fact that we can incorporate this information with ICT, information and communication tools, and be able to communicate the information in real time, either to caregivers or to other professionals or to family members, and that will lead to connected sensing. Then there is the very important fact of non-obstructive sensing. Okay, nowadays many of you are wearing the smart watches, and they are very smart. They are good. They detect your heartbeat, they detect your oxygen level, they detect so many other things. But you have to always wear it on yourself, which is not very convenient at all scenarios. So non-obstructive sensing is something that means it is remote. So you don't have to wear something. It is fitted somewhere else, and it is able to sense your information and help you based on the need. So general communication devices need to be optimized to fit the constraints of size and electromagnetic emissions. And finally, radar normally works in the microwave and RF ranges. So we are looking at non-ionizing sensing. That means what? As I already said, the traditional methods that we use for X-rays and similar technologies, there is a chance that we will be able to replace all those with a radar sensing. So these are some of the benefits that we are looking forward to in terms of radars in biosensing. Now, if you want to discuss the types of architecture, by itself is quite an elaborate discussion. I'll just keep it brief here because I made this particular presentation application oriented. So the types of architecture that we focus on, one is the time domain method, and then we have the frequency domain methods. Time domain methods are also known as ultra wideband radar or impulse radar. So they look for a time information by sending very narrow pulses in time. So that's the time domain radar. On the other spectrum, there are different types of frequency domain radars, and two of the most commonly used ones I have listed here. One is the stepped frequency continuous wave radar, and other one is frequency modulated continuous wave radar. So both of them are useful in their own ways. FMCW radar is very popular in terms of higher frequencies. It is also used in terms of through-wall imaging. There is a lot of FMCW radar is used. Stepped frequency radars are also in the similar range. And as I said, I will not get into the details of the architectures at this point. I'll first focus on the applications of this. So applications, let's see what are the different applications we can think of. And obviously this list is not going to be complete because there is always newer and newer ideas that come to mind and people are implementing such ideas. But on the broad, the applications of bioradar are in health monitoring. So this is something that is the personal health. We can monitor ourselves or for monitoring in the hospital environment. Then the next most important thing that we do with this bioradar is search and rescue operations. So search and rescue operations particularly refer to the fact when, let's say, there is a natural calamity like an earthquake or a building collapse. So how do we find the survivors under the rubble? So for doing that, traditionally there are other methods and most of them involve digging up the rubble. But nowadays people are using this radar, bioradar, as an alternative to digging through the entire rubble to finding survivors. So that's the very important application. Then there is clinical diagnosis that is happening. Different types of diagnosis I will talk about also. Some of them involve even bacterial identifications have been tried with this type of radars. Then bone health is a very important thing that we do. Glucose monitoring, that is something that we try to do. So clinical diagnosis. Then military operations. In military operations, basically there are various police activities that happen, police and military, and they may use some different types of radar for identifying the terrorists, let's say. So when there is a hostage situation, then what would they do is they will go ahead and use a radar, a through wall radar, and they will try to identify who are the people that are behind the wall, are they having weapons, and so on. So this is part of military operations, and similarly for security also. But in this case, this is pointed out to the fact that even for personal houses, we could be able to think of such a scenario when the doorbell rings and you watch through the eye hole and you don't see nothing. But if there was a way, you must have surely wondered, if there was a way I could just look through the wall, and that way is there, it is developing. And that is a picture that is shown. Just look through the wall and you see what is available. And also the other use of this is in airport security. Now people are looking towards radar for airport security operations. So that's another application. And here next one would be the last one that I listed, is the human machine interface, HMI. HMI is very, very popular when we talk about this or sophisticated glasses. We are having different types of companies making different types of glasses, and we can do various things, control various programs, let's say apps with that. So that is something that falls in human machine interface, and radars are going to be very, very useful in the future for that. Gesture recognition and human activity recognition, these two are primarily looked into in terms of radar, and they are going to help us build our HMI or human machine interfaces. So these are some applications of bioradar. And rest of the presentation, I am actually going to show you some details on the research that has been going on, and a few other information regarding the issues of the bioradar. So let's first of all look at health monitoring as an application. So health monitoring can be of various types. I listed a few of them that just came to mind. Let's say microwave thermometry. When last 2 years we have had so many thermometers, why not microwave thermometry for remote sensing of temperatures? Yes, that's possible. Then the primary way we look at health monitoring is obviously vital signs information. And what is that? The heart rate and the respiration rate. So these two are very critical in terms of vital signs. Then there is apnea monitoring. Apnea monitoring is basically the sleep disorder monitoring. So there are certain aspects of sleep disorder that can be monitored when we look at the respiration and the heart rate of an individual. So apnea monitoring and glucose monitoring Glucose monitoring is done with based on a radar again, using that sweat information. From the sweat information, we can somehow be able to monitor the glucose. So these are all the last two at least are very current research works. People are working in those. I'm going to talk about the vital signs monitoring as we can use it. We can use this in medical facilities, as I already said, in ICUs. We can use this in homes, particularly when we have special needs patients and elderly individuals in the houses. Becomes important. It can also detect the fall, and it can inform the next of kin, let's say, if some emergency happens. And it is also used in pediatric care. One important application that people have talked about is SIDS, sudden infant death syndrome, which kind of people are working on to be able to put the benefits of Bioradar in that. So these are some of the health monitoring places. Now let's see what is this. So here we have a picture of a person inhaling and exhaling. So when we inhale and when we exhale, our body movement that happens, the slight body movement that is happening, this slight body movement is actually what gives us the information on the respiration rate as well as the heart rate. So this radar captures this chest movement, and what is displayed is something similar to this. So you see there is a similar to a sinusoidal wave, and obviously there is a lot of noise here. The reason being that it is taken in an open environment, the measurements are taken. So on this particular noise, if we are to magnify, since not all noise, it is also some information. What is the information? This heartbeats. Heartbeats are some interesting information that are modulated onto this sinusoidal wave. So we are able to actually identify the respiration rate as well as the heart rate by capturing these movements, the chest movements. And this heart motion, obviously we need a very high resolution radar to capture those. Otherwise, we wouldn't be able to see this. I'll show you an example. Now, one important thing that happens here is that if you've seen that there is so much noise here, the information is really not very clear. So there is a lot of pre-processing that happens to be able to extract any useful information from these types of radars. And for doing that, there are a whole list of methods that there a question. Okay. So there is a whole list of methods that people have proposed for this purpose, and basically what is to be done is we need to do some subspace extraction using, let's say, singular value decomposition is a popular method, SVD. And after that we need to remove the effects. Here I written wall effects. It may not be wall effects, it may be just some other surrounding effects that are present. Then after that we need to also remove the background clutter, which is stationary in nature. So removing the background clutter, and finally we will be smoothening the radar echo matrix. So this is a flow of that particular process. Here is my raw radar echo. See, nothing is really visible here. If you compare this particular picture with the one on the other side, nothing is really visible. But what we did, we taken this raw radar, we processed this, and in the space of processing, we got rid of the, as I said, we got rid of the wall effects or other effects, surrounding effects. We extracted the subspace. We removed the background clutter. And finally, we did some target identification. Here is the target chest displacement. So this is the kind of processing that is involved. If you look at this first raw radar, you'll just not be able to identify anything, but it carries a lot of information. This is an app that was designed by one of my students for this particular purpose. And at a particular time, you can see that the target range is visible, and as well as the target chest movement is visible here. So from that particular raw radar info, we are able to extract the range information as well as the vital signs information. And while doing that, one more thing that we always talk about is something known as a micro Doppler signature. You all know about Doppler. Doppler happens when there is a movement of the target, and when the target moves, we get a Doppler. However, microdoppler happens when there is a minor movement of the target which by itself is moving. A popular example of this is the chest movement. So a person is walking around and at the same time he is having his chest movement. So the chest movement will become a microdoppler effect.
इलेक्ट्रिकल डिपार्टमेंट से आपका पास मीन्स आप लोगों के पास कुछ रिक्विजिशन गया है कोई 4 एसी के लिए हैं तो उसको
So
थोड़ा
that
जल्दी कर
is.
दीजिए ना
So I see there are some questions. We will get to that at the end.
हो गया डायरेक्ट तो ले सकते हैं क्योंकि आप लोग तो डायरेक्ट लिए ही कुछ
I think Professor Shuman there. Again, let's continue. I'm sure he will notice that. So why I talked about this is that here is a graph that I have. Okay, the first few results were using an ultra wideband radar, and currently this particular one I'm showing using an FMCW radar. So you can see the information that we get is pretty much similar if we know what is the processing to be done. So here I'm showing you another version of the vital signs detection. Here you see the person was located at this level. So this is a range Doppler plot. And on the range scale, you can see this yellow information in spot. The person got located here. And the micro Doppler is basically a sinusoidal curve that you will see at that particular range scale. And based on all the information generated, we have performed music, a pseudo spectrum we obtained, then we extracted the frequencies from there, and those frequencies are converted to what is the respiratory rate and the heart rate. So this is for a particular subject who was detected, and the respiratory and the heart rates are extracted. Now, the similar information can be used for diagnosing different sleep problems or different other irregular breathing problems. And this is a list of all the problems that could happen. Like this, here if you notice this particular, there are minor gaps between the particular waveforms that are appearing. So we can be able to detect this pauses. We can be able to detect longer pauses also, and all the other things like these variations in breathing can be detected, and the person can be informed of that. So this is the, just a minute. So this is the case of health monitoring that we just discussed. Now looking at the second most important application of this that I listed is the search and rescue applications. And I already talked about that in brief, that we can use it in through-wall imaging, in post-disaster surveillance and rescue, as well as in accident detection and prevention. This is even useful in the automobiles. So let's show you an example or a case of this when the subject is beneath the rubble. So this is a picturization of a bioradar placed on top of the rubble, and the survivor is somewhere inside. And this is our in-lab experiments that we did. Obviously, we can't dump rubble on a person. So this is a radar placed on top with some rubble and the subjects underneath. When we do that, we see initially, if you watch this, we see nothing initially. This is the raw signal. And this is the ultra wideband radar, and this is the raw signal that we obtain. So initially it seems like nothing is really there, but then if we are doing some pre-processing, which in this case is taking the variance of this raw signal, what we start noticing is that there are significant peaks appearing at different ranges, and these particular ranges actually correspond to the different subjects that are present. So this is a measurement that we conducted on different subjects. On this side, you see the particular layers that are actually present. The theoretical study of this was also done based on the different layers that should be present, and their permittivities and their losses all have to be taken into account when we need to get this particular information out. Here is one more particular view of that. There is the wall responses here, which we can think of some kind of a rubble response, and then finally the human's reflection. So these are some results from the detection of subjects. Another important aspect is to know how many people are present. So we say people are present, fine. How many people are present? That is also important in these scenarios. So for that purpose, we employ a very similar approach. We use a radar, we detect the range Doppler, we do pre-processing, we take variance and the singular values. Then after that, we actually feed it into a machine learning algorithm. And once this machine learning algorithm looks at the data, it is able to identify whether there is one or two or three subjects present. So that is the other way of looking at it. So if you see this radar echo, there are two targets in this case. This is the radar echo. Again, nothing really is visible on this particular scenario. So we did a lot of pre-processing. Pre-processing reduces the background clutter. It reduces much of the noise that is present, and it gives us some information which then is processed for its variance and the singular values. So this is clearly visible here that when there is one subject, we get a lower variance than two subjects and three subjects, and similarly goes for the singular values. So this particular information, either it can be deducted and we can conclude from this, or other option is feed this information into the machine learning algorithm and get more concrete classification. So this is in terms of people counting. And next, the clinical diagnosis aspect is another very huge challenge that has been addressed. Some of the examples of this are in blood and cancer cell analysis. Cancer diagnosis is a huge area which is used with radars, and there is a lot of information you will find on this particular area also. Then there is bacterial identification, which is done using this kind of radars, and the bone health diagnosis. I'm going to talk about this last case for a bit. Yeah, this is about cancer detection, and you can see there are various ways. One of the oldest ways is microtomography, and but nowadays we are thinking of using a less exhaustive method in which we will do simple UWB radar based imaging. Time reversal we will do. So basically there is the transmitter and there will be receivers. So when there is no formation, no cancer, there will be a particular signature which goes to the receivers. Whereas on the other hand, if there is a tumor present, that will change the electromagnetic characteristics which reaches the receiver. And by comparison, we will know that there is some kind of a malignant tissue present. So this is the way cancer detection progresses. And then bone health. Bone health is again the particular stages of osteoporosis we want to detect through this particular method. So what is osteoporosis? I think I'll come back to this slide later. Osteoporosis is the loss of calcium. It is not only age related, as people have standard knowledge. They think that it's age related. It can happen due to various reasons in various individuals. And what basically happens is, if you see these three figures, there is a loss of the bone mass. So when there is a loss of bone mass, obviously, if you are having an electromagnetic wave passing through this, it will be either absorbed more or less depending on the mass that is present. So this idea has been taken up and converted into a bioradar system for osteoporosis detection. These are some of the standard methods, and the reason for highlighting them is if anybody wants to get their bone health checked up, the methods are very cumbersome, very expensive, and hardly available. So DEXA, I think there is only one or two machines that will be available in a particular location. Depending on how big the place you are talking about, but this is the most standard way of finding out your bone health. The other methods are also present, like QCT, qualitative computed tomography is there, MRIs are used for this purpose, and the smallest machine that does this work is an ultrasound. But ultrasounds are not at all useful for this purpose because they actually cannot penetrate through the bones. So the actual information they give is very limited. So that's why we need to look at alternative methods. However, in the process of looking at alternative methods, one very important fact that came up, and this is true for all bioradars, is that this particular tissue, the body tissue that we are looking at, is not a very simple dielectric medium. It's got very high loss. And when we are passing this, if you see this simulation, basically we are sending a signal from this end, and there is a very high signal present at this port. But when it passes through the tissues, this wrist sample, the information, the waves that are present on the other side are very small, very low. And this is also shown here. At 2 gigahertz, if you simulate this depth of penetration, the signal strength, this is shown in. See how the signal strength is falling from skin to fat to muscles and bones and farther on. So basically at the other end, we would get a very negligible amount of signal passing through. This in turn creates a lot of problems in diagnosis which are being addressed. So here is some results that we have obtained from the healthy bone. And then when the bone gets slowly deteriorated, this is a signal passing through a wrist sample from 1 to 3 gigahertz. This has been taken, and you can clearly see there is some variation that happens in each of these samples, although the variation is very small, because here we are plotting in terms of dB, and this is minus 20 dB, minus 15 dB ranges. So it's a very small variation. And similarly, the absorption, if you watch the absorption, almost the entire signal is getting absorbed by these samples. However, still there is a slight variation in the 3 samples, and this information is taken up. And these are some dielectric properties of the human tissue that have been used for this purpose. And if this information is taken and processed, then ultimately, again, this is done using a machine learning. We take help of machine learning whenever the information that we have is not very concrete. So here, taking help of that and some other statistical methods we have taken help of, we are able to actually look clearly at the different variations of the bone from a healthy bone and how it degrades down to a osteoporotic bone. So this is about bone health diagnosis methods. Finally, I'll talk about HMI in brief. HMI, as I said, is about gesture recognition and human activity classifications. Gesture recognition is a huge area which you can find lots of information. I'll show you a bit on human activity classification. So this is these are actual experimental results that were obtained using a radar. And there are 4 case scenarios that are shown here. The 4 case scenarios are on the same individual. However, the difference is that he was either sitting idle, or he was reading loudly, or he was doing deep breathing, and this is using pranayama. So you can see clearly that just without any much further processing also, we are able to clearly get an information as to the status of the human, and based on this human activity, now further actions can be taken on different devices. And this is the spectral analysis of the same plots. Again, the 4 particular cases are shown, and the spectral analysis reveals us the frequencies basically of the different respiratory samples that we obtained from the same individual. Again, this particular information can be put to the machine learning process, and the accuracy that we obtained is pretty good, given that this all was done on an actual target, actual human sample in open space. So there was a pretty good classification that was obtained based on these 4 activities. Now coming to why artificial intelligence was used, and this is something that you know. Why artificial intelligence? Because we want to make our radars intelligent. And why they need to be intelligent? Because we want them to operate autonomously. We don't want to interfere in their operation all the time. So they need to adapt to the changes in the environment. And to adapt to the changes, they need to perceive the environment. So these are some of the reasons why machine learning, for example, need to be implemented in certain cases. So we have to do a comparative analysis, and we need to train the particular radar. Now we have a software defined radar, so we can train it based on our learning, and we can ask it to do different tasks. We can connect different devices along with it and have that do different tasks for us. So this is why artificial intelligence came up here. And finally, some issues. Obviously, there is nothing that doesn't have its inherent problems, as we say, and Bioradar also has its inherent problems. What are the problems? First problem is attenuation, and I have shown this to you when I was talking about bone health. The attenuation is very, very large. So hardly any signal passes through the body, which is a highly lossy media. So this is a major problem that needs to be addressed. And obviously we can change the media in this case. We can just say, okay, let's drop the media. No, we are talking about a human being. We have to work with it. So we need to make more efficient systems. We need to make more efficient signal processing for this particular scenario. And that is what is the second issue, very complex signal processing. Why? Because the particular information is very, very subtle in nature. There is subtle modulations of the echo signal, like when I was showing the heart rate information on top of the respiratory rate, on top of the sinusoidal wave. the information is so subtle that you need to think of very complex signal processing algorithms to be able to achieve your goals. And finally, the third major issue that these bioradars are facing is its short range. Short range is obviously because, again, attenuation, but there is also another factor for this short range, and that is the radiation regulations. See, we are talking about a human body, so obviously the radiation needs to be very limited. So not just that the signal deteriorates very fast, it is also that the signal that we send is very low, because we need to comply with all the regulations. Let's see what are the regulations. So first problem I said was attenuation, and this is some of the body some of the materials of the body that are present, the permittivities and conductivities. Based on this, the attenuation is shown on one side and the penetration depths are shown. So you can see how clearly it falls off and the attenuation rises up as we go in over the frequency range for the different materials. Next problem is the complex radar echo, and to highlight that I have again pulled up a picture which I have shown earlier. If you see here, nothing really is visible even after pre-processing. So we need to think of complex algorithms for achieving our goals. And finally, the regulations. So when we talk about regulations, you all must be aware of the wireless standards, and there are newer standards which may have come up after this, what I listed here. This is only for 2.4 gigahertz. Now we are looking at higher frequencies. There are different standards for that. But let's focus on the lower table, which lists some standards for medical applications. And all our bioradar has to somehow fit in with these standards. For that purpose, there is this MICS, which is the medical standards that have been specified. There is the ISM bands, which is the, again, mostly used for medical application. Then there is the telemetry bands, which are also being fixed by the different IEEE standards. And then there are the ultra wideband bands, which are popularly used. However, if you can see, the power levels on all of these are very low. So whereas in the case of a standard wireless system, you are able to transmit up to 24 dBm of power depending on what the purpose is. But in these cases, for medical applications, the transmitted power is very low. For ultra wideband, the transmitted power is limited to minus 40 dBm. So obviously you are sending very small amount of power. On top of that, there is a large amount of attenuation. So you can understand the problem that arises is that we get very, very short ranges on our applications. So these are some of the issues that people have faced while they were working in bioradars. However, as you have seen through the different examples that I've shown you, people have found, researchers have found different ways out of achieving their goals. And at this point, there is a huge potential that is lying ahead for these radars in biosensing. And there are problems. For example, another problem is the proximity of the human body. And proximity of the human body not only leads to attenuation, it also changes the signal a lot. So we need to keep that in mind while we design the antennas, let's say, or while we design our transmitters and receivers. So that is the challenge that these radar designers are working on. However, the potential is unlimited. If you can think of some use of a bioradar, you can try it. That's what the current trend is. And every other day a new paper is published in this area talking about a new application of radar in biosensing. So if any of you are interested, you can look that up. I also didn't put a reference slide because there are a lot of references that I wanted to put, but there is no point of putting reference slide. When you can't note them down, anybody who is interested can always contact me, and I will be happy to guide them on these applications. So I'm very happy to be able to deliver this lecture today. Thank you for all your attention. And I think that's all that I wanted to talk about today also. Let me on my video. Yeah. So that's all of my presentation. So now if any of you have any questions, I'll be very happy to take the questions.
So if anyone have any question, please raise your hand. Or ma'am, there is a 2 question in the chat box.
Yes, there is a question in the chat box. Can it be used for workers working in hazardous areas? Yes, actually, hazardous areas. I don't know if the person is still here who asked the question. What he actually means that I don't know, but I'll give an example anyways. So for coal mines. So this particular radars have actually found a very good use in coal mines. Okay, Mr. Faraj, I think he's there. So you can ask the question if you want. Otherwise, how I would address this is that there in these coal mines, you know what is the problems there. The health of the miners is of very importance. So people have tried to lay out a complete system of radar sensors. Obviously, this is wireless, so that's the benefit. Wireless means we don't have to lay the wires, so we have to place the sensors here and there. We can place the sensors on the miners themselves, and it has been seen that that actually benefits their work environment also. So that is one important use that has been done. And then again, search and rescue is there, as you can see. So if we have miners wearing radar sensors on themselves, we can easily find them if some calamity happens. So that is the other reason why that was proposed. And in some cases, it has been implemented, particularly abroad. They have tried to implement this. I'm not sure about the Indian context, how much it has been done, but yes, it's possible. Okay, I hope that answers your question. And there is one more question I see. Can I use accelerometer to estimate respiratory activity in radar echo pre-processing? So see, Madhusudhan. Okay, Madhusudhanan. Well, accelerometers are used already for different types of respiratory activity detection. However, here the purpose that we have is particularly to not have any particular on-body sensors. So our purpose of radar is mostly to make it remote, so that the person doesn't have to carry it. Just now I said minors can put it on, yes, because that's a specific scenario. But in other scenarios, like inside the house, we don't want a person to always be burdened down with some kind of a sensor. So that's why for this particular what you asked is about the respiratory activity. We don't really need an additional accelerometer for that. We are able to detect this using the radars that are already available. Respiratory signals are the easiest detected. Then after that comes more other information like the heart rate and all. So yes and no, you can use accelerometers, but there is no real need to put that in place. Okay. So yeah, Shubhasri wants to ask something. What's your question? Yes.
Thank you, ma'am, for your.
Yes, Shubhasri, you have a question?
Yes, ma'am. Yes.
Shubhasri, you may ask.
Yes. Actually, I want to know that.
Shubhasri?
I think her voice is very low.
Am I
You
audible?
can type the question otherwise.
Okay, ma'am. Okay. Let me type.
Ma'am,
Yes, yes.
yes, I am asking on question in continuous means in continuation of your previous answer that if we use for working in the hazard area, different area that you coal mined. So basically in the coal mine when we are using the wireless and if we see the exact scenario, the wireless coverage over there is very low. So in this case, how will it will cover? Because most of the case, if we want to plan any your base station or tower, so normally the service provider will not use any tower over there because there is no population is there only for few or company individually for suppose any coal mine. So this area totally there is a the population is very low. So
Yes,
if I
yes,
so in this
yes.
case, how the coverage of the wireless network will be done over there?
Yes, yes. So, well, actually, when I talked about the coal mine issue, the solution rather, that wasn't based on the standard wireless network that we are available. So, for that particular scenario, for such a scenario, we wouldn't be using a we wouldn't be using the network that is available. We have to create our own network, like we create networks inside different buildings, let's say. So it has to be a dedicated service for this purpose. And even if you have this network available from the towers, that wouldn't be strong enough to penetrate through the layers of the earth, because the layers of the earth create a lot of attenuation again. So we wouldn't be able to get any signal underground because there is so much attenuation happening. So basically in a coal mine, that is one of the most problems that is happening. We can easily put sensors inside the mine. We can put sensors on the particular individuals, but then the signal has to reach from above the ground to under the mine, for which purpose we need to create a dedicated transmitter receiver on top of the particular ground level, and that should do its own dedicated network for transmission and reception. So it wouldn't work on our standard mobile networks. So that is the problem, and for that purpose only there is a sluggishness in implementation, I think, in this type of scenarios, because to create that is itself an entire cost aspect is coming in. It's a huge area. We need to create a huge network for that. So that's why this particular there's a stalemate, let's just say that, in terms of mining industry in India, that this hasn't been really taken off. So yes, Professor Shuman, you are completely right. This is a major challenge in the fact that we wouldn't get any signal underground. If we go underground, no signal is there. But radar by itself, if you think of radar, radar is sending a signal. And if the signal is in the right frequency, in the right signal strength, we are able to even transmit it a few hundred feet below the ground at least. So that has been proven. We are even doing this ice under ice explorations with the radar. We are doing archaeological explorations. Different aspects have been done with radar, but however, for this mining aspect, it is it is difficult, but theoretically it is possible. Let's just say that. Is that answer your
Yeah,
question?
thank you, ma'am. Yeah,
Yeah.
yeah, yes, thank you, ma'am.
Yeah, sure. Shubhasri has asked, can we use this bioradar to detect animals? As the name is bioradar, obviously you can use it to detect animals. It's bioradar. Why not animals? If we can detect humans, we can detect animals also. Yeah, and actually, thanks to Shubhasri for pointing that out. I should have also highlighted a few aspects of bioradar on animals as they are used. Yes, for counting cattle, This is something that has been proposed for counting the cattle. So basically in terms of RFID also, this is a similar concept, radars and RFIDs. So we are putting different tags on the cattle also for that. We don't really do vital signs detection of animals, so that part is not yet investigated. But in terms of search and rescue, it has been proven that even, in fact, my student also looked into that. What if instead of a human being, there is an animal under the rubble, what it will do? The signature will be different, and it is completely possible to identify the animals also under the ground. Okay, is that
Thank you, ma'am.
Shubhashree, is that okay?
Yes, ma'am. Thank you, ma'am.
Yes.
Thank
Yeah, so it's possible, and thanks for pointing that out. I should include that part in my PPT.
you. Yeah, ma'am. Okay.
Okay.
Okay, thank you, ma'am. I think there is no more question is there.
Yes. Yes.
So